Another type of deformation occurs when an object is subjected to a force parallel to one of its faces, while the opposite face is held fixed by another force. The stress that will cause this deformation is called shear stress, denoted by letter S. It is defined as the ratio of the tangential force F to the area A of the face being sheared. To illustrate this, consider a rectangular bar which has a height h. The top face, which has an area A, is free to move, while the bottom area is considered as fixed face. When we apply a parallel force F at the top face, the top side will be sheared to the right, since the fixed face at the bottom will experience a reaction force negative F. Therefore, the top face moves to the right relative to the fixed face. The shear stress on the top face is equal to the shear or tangential force F, divided by the sheared area A. We see that, if the object is originally a rectangular block, a shear stress results to a deformation delta x, parallel to the sheared area, such that the front face becomes a parallelogram. The shear strain, denoted again by the Greek epsilon, is defined as the ratio of this deformation delta x, and the height h, of the rectangular block. We discuss in part 1 of our discussion, that the strain is proportional to the stress. The proportionality of the shear stress and shear strain can also be observed in relatively small amount of stress. The proportionality can be described by a constant called shear modulus, denoted by S sub m. Mathematically, shear modulus is equal to quotient of shear stress and shear strain. In the same manner as Young's modulus, shear modulus is also an indicator of body's elasticity. Table below shows the values of shear modulus for different substances. Among these substances, tungsten is the strongest material to any shear deformation. If we apply the equations for shear stress, shear strain, and shear modulus, we can derive for an equation that defines shear deformation delta x as the product of the shear force F and height h, divided by the product of the shear area A and shear modulus S sub m. Take note of the SI units of each variables. Force is in newtons, height should be in meter, area is in square meter, shear modulus is in Pascal, and deformation is in meter. Another thing that we should take into consideration is the shear strain in bolts. Bolts may also experience shear stress and strain. Imagine a bolt of diameter d is being used to join two metal plates. When the two plates tend to move in opposite direction by means of forces F and negative F, then the cross-sectional area A of the bolt will experience a definite amount of single shear stress. Single shear stress is expressed as the shear force divided by the shear area A, which is pi over 4 d squared, wherein this d is the diameter of the bolt. Double shear may also occur in bolts, if three metal plates are joined. In this case, two cross-sectional areas will be sheared, hence the total affected area is twice the cross-sectional area of the bolt. Therefore, the double shear in bolts is expressed as the force applied in the plate, divided by the total shear area, 2a. Shear stress is also exerted when punching a hole in a metal plate, just like when we are putting holes in sheets of paper using a paper puncher. This photo shows punching holes in sheets of paper using a paper puncher. This sheared area creates a hole in the paper. Imagine, a punch of diameter d is being pressed with a force F into the surface of a metal plate of thickness T. As the punch penetrates the plate experiences shearing stress until a cylindrical piece is removed from the plate, hence creating a hole in the plate. The sheared area is equal to the circumferential area of this cylindrical piece. Therefore, the shear stress in punching a hole is given by the expression shear force F, divided by the shear area pi times the diameter d of the hole, and thickness of the plate T. Now, let us answer this problem. Problem number 2. A rectangular copper bar of dimension, length 10 cm, width of 5 cm, and height of 5 cm, experienced 10,000 newtons of opposite forces, parallel to the plane of length and width, at both upper and bottom surfaces. Determine the shear distance of the upper surface relative to the bottom surface. Imagine, this is the rectangular copper bar that measures 10 cm in length, and 5 cm in both width and height. If we apply opposite forces on the top and bottom surfaces of the bar, with magnitude 10,000 newtons, the bar will be sheared with this distance, denoted by delta x. And this is what we are going to solve. The shear modulus is 4.2 times 10 raised to 10 pascals. Now, to solve this deformation, we will use these four formulas. Strain equals the shear distance delta x over the height h. The shear modulus equals shear stress divided by strain. We will also use shear stress equals force over the sheared area, wherein the sheared area is the product of length and width of the bar. Combining these four equations show the shear distance delta x is force times height divided by the quantity, area multiplied by the shear modulus. Substituting all given information, so the shear distance is only 2.38 times 10 raised to -6 meter. This is so small that you cannot even notice it. But in designing complicated and precision machines, this size is important that could somehow affect its performance. Let us give one more problem about shear stress. Problem number 3. Letter A. Determine the force to single shear a steel bolt of diameter 2 cm, if the stress applied is 800 megapascals. Letter B. If this force is applied to a bolt subjected to double shear, determine the shear stress developed in the bolt. Imagine these two plates are joined together by means of a 2 cm or 0.02 meter diameter bolt. The forces exerted on the plates causes a stress of 800 megapascals of stress. What we are looking for is, letter A, the applied force, for a single shear, and letter B, the double shear stress. Now, let us solve for the shear force. We use the formula of stress, shear force over the area, wherein the shear area is equal pi over 4d squared. Substituting the given information, so the shear force is 251,327.4 newtons. Letter B, double shear in the bolt will happen only if there are three plates joined together, wherein the upper and lower plates are pulled in the opposite direction of the middle plate. From double shear stress formula, force over twice the shear area, and the cross-sectional area is pi over 4d squared. Then using these two equations, we solve for stress, so the bolt will experience a shear of 400 megapascals. Obviously, this value is half of the single shear since the affected or sheared area doubled. Now it's your turn. Answer this exercise number 1. A steel punch can be worked to compressive force of 141,372 newtons. Find the least diameter of the hole which can be punched through a steel plate of 10 mm thick, if the ultimate shear stress of the plate is 300 Newton per square millimeter, or megapascals. Congratulations for reaching this topic. The last part of this course unit deals with the bulk modulus, the volume elasticity. Unlike tensile and shear stress wherein the deformation deals only in one dimension, the volume stress deals with the volume of a solid body. The volume of a solid body may change if stress is applied on all sides of the body. Imagine a cube of initial volume V sub I. Increasing the compressive force by delta F, on each side, will also increase the stress on each side. This stress is called volume stress. This volume stress is equivalent to the change in pressure delta P, on the surface of the body. It is defined as change in total compressive force delta F, per unit surface area A, of the body. The degree of change in volume of a solid body can be determined by the quantity called volume strain epsilon. It is equal to the change in volume delta V, divided by the initial volume V sub I. The proportionality relationship between volume stress and volume strain can be described by a property of matter, called bulk modulus, denoted by letter B. It is defined as the ratio of volume stress and volume strain. The table below shows the values of bulk of modulus for different substances. In this table, we can see that tungsten still has the greatest value of bulk modulus. If we apply the equations for volume stress, volume strain, and bulk modulus, we can derive for an equation that defines the change in volume delta V as the product of the change in total force delta F, and the initial volume V sub I, divided by the product of the surface area A, and the bulk modulus. Congratulations for reaching this last sample problem. Problem number 4. A solid brass sphere is initially surrounded by air, and the air pressure exerted on it is 1 × 10⁵ pascals, normal atmospheric pressure. The sphere is lowered into the ocean to a depth where the pressure is 2 × 10⁷ pascals. The volume of the sphere in air is 0.5 cubic meter. By how much does this volume change once the sphere is submerged? So imagine this is the ocean. Above the ocean is our atmosphere. The atmospheric pressure is 1 × 10⁵ pascals. This is also the initial pressure exerted on the solid brass sphere of initial volume 0.5 cubic meter, when it is exposed to atmosphere. Once we submerged this to the ocean, this pressure will become 2 × 10⁷ pascals. The bulk modulus of the brass is 6.1 × 10 pascals. This increase in pressure somehow will cause the solid brass to change its size or volume, and this is what we are looking for. Using these equations simultaneously, change in volume is equal to change in pressure, Pf minus Pi, divided by the bulk modulus B, multiplied by initial volume. Substituting the values, so the solid brass is compressed by an amount of 1.63 × 10⁻⁴ cubic meters. This is so small, that is why solids are considered nearly incompressible.